Let's look at soils investigations. So we're going to take a look at why you would want to test your soil. This is actually a picture of my old back concrete slab outside the back of my house, and this is why you want to test the soil and make sure that you have a firm foundation. Buildings are supported by soil. Engineering properties of soil are highly variable, and they need reliable soil information for structural and site design. So if the soils were not compacted here, which likely they were not because this is not a structural piece, then slowly they'll sink and sag, and then, sad for me, I had a broken concrete slab. So, knowledge gained from soils investigations allows engineers to make estimates for bearing capacity of the soil. How much load can you put on that? How much it's going to settle that foundation? The earth pressure. So, earth pressure being against the sides of the building. If you build your foundation underground, usually you would dig out, however far you need to dig out, you put your footings under the surface level. Well, then when you backfill all that dirt in, it's going to be pressing in on those walls. So soils engineers and soils investigations can give you earth pressures. Drainage characteristics, also wastewater disposal limitations, and we've talked about wastewater already a little bit. So soil, this would be a good thing to make sure you note here. Soil is made up of 45% mineral, that would be sort of like your rocks, 25% air, 25% moisture or water, and then 5% organics. That's kind of like your decomposed leaves and um, other things, twigs, other things like that. So we don't call it dirt, we call it soil. That's a big difference. In engineering, it is not dirt. Here are your minerals. Your minerals are divided into gravel, sand, clay, and silt. And you're going to actually subdivide those into those four pieces and determine how much you have of each. That's what you're going to do in your soil survey. So the USDA has a web soil survey online where you can get some information, and that's one of the places that you're going to go. This is what you might see if you're a soils engineer, a soil boring log. And it is kind of lame, but it's not that boring. Wink, wink, because boring means going down into the ground. That was awesome. So we have a depth here. They went 22 feet down into the ground. So you would have to have a giant drill to go down into that far, and it's just hollow, so it just cores out a giant sample. You take that core out, and then you test different depths. So they tested these different depths, and then they grade them. And I'm going to show you how to grade at any particular depth. So you would be doing just kind of one of these samples, and you may end up with a grade that is one of these code letters, which you learn about, and a description of something like this. But this is what a log might look like for a full boring log that goes down to 22 feet. Coarse grained are described by their grain size, like bigger rocks or smaller rocks. Fine grained, like your clays, are described on the basis of their plasticity, how much they kind of flow and move. So we have these sieves, and you're going to use these. We're not going to use this many. We have two different sieves that we're going to use, but it will allow smaller and smaller particles to sort of pass through, and that's how you grade it based on different sizes here. So these are the sieves. Again, we only have two different sieves and a pan that we place them into. So a number 4 sieve, for example, is a 1/4 inch square, and they're calling it similar to hardware cloth. And again, you're going to be using some of these. A 40 sieve, which is the other one that you're going to use, is similar to a window screen. So we're using a number 4 and a 40. And then here's your grain size. So number 40s are going to be down here into the silts and fines. And your number 4, that's moving up into here into your gravel. So we're basically breaking it down from gravels, sands, and silts, and then clays. That's kind of the regions that we're separating into. We're going to have 3 different grades. And so this is just showing some relative sizes, pea-sized here, rock salt, looking at the pennies, sugar down to here, and then clay is even finer. You can have different graded soils. Again, a coarse grained soil is defined by the particle sizes and the distribution. A well-graded soil has all different sizes. A poorly graded soil has uniformly, maybe they're all the same size, or there's gaps where there's a few of the sieves are totally empty and a few of them have a lot. So that's the difference between poorly graded and well graded. Clean soils have little to no fines. There's less than 5% of fines. So it's mostly gravel. Dirty soils contain an appreciable amount of fines, more than 12% of silt and clay and things like that. And looking at plasticity, so just a few other things to add to your notes before we get started on the project. Fine graded soils are classified by the plasticity of the soil, and that refers to the consistency of fine grained soils as water content varies. So as we adjust the water levels, then plasticity is going to change. And we'll take a look at that a little bit later here. So we have different soil types. These letters correspond to the soil types. And since sand is already used, S, silt is an M, and so on. And then your gradation, well or poorly, and your plasticity, high or low. So we combine these letters, and then that's how you get your soil classification. And that can then be used for the engineer in designing the footings. So a coarse-grained soil, granular soil, has more than half of the soil grains visible to the naked eye. So that means they're larger, right? If the percentage of gravel and sand is greater than 50% of the sample, it's coarse-grained. So in our sieves, if 50% is gravel and sand in our first two sieves, then it is coarse-grained granular. And since we only have three sieves, if more than 50% goes into our pan, then it's a fine-grained soil, and that's mostly silt and clay. And knowing where we live in Colorado and how much clay that we have, you may be able to guess ahead of time what we're going to end up with, but you're going to actually test this out. So in addition to sieve analysis, the following tests are performed to determine plasticity. So you can do a dry strength, and that's where you test it by crushing it. You can do a dilatancy, which is shaking it, or a toughness. We aren't going to do these. We are just going to be grading them based on what goes through the number 4 sieve and the number 40 sieve. So for foundation, sand and gravel, absolutely the best. Medium to hard clays, decent, it's good. Soft clay and silt is poor. And organic silts and clays is undesirable. Peat, or that permafrost type stuff, you cannot build on. It's terrible, terrible, terrible. So depending on what you have, this is your allowable bearing pressure in pounds per square feet that you can actually place on there. So if you can't put as many pounds per square foot onto a footing, you need to have a larger footing that gives you a lot larger area. So for poor soils like clays, you have to have a lot larger footing to support yourself. If you're on bedrock, you can build a building on a pogo stick, and it's going to be awesome. It's not going to sink into it. But then you look at your drainage, and you can see bedrock is terrible drainage. Gravels is really good. So gravels and gravels with fines makes really, really good foundation type materials to build your foundation on. And that's where we're going to end it. Now it's time for you to actually do the soil engineering.